effective constructions. Okay, fine, I'll be talking about effective constructions of EC groups, so EC meaning existentially closed. Okay, so existentially closed groups were introduced in the 1950s by W.R. Scott, no relation to me. And from the best of my knowledge, he was interested in sort of well, I was going to say generalizing, but he constructed them, or he introduced them in analog with algebraically closed fields. And maybe his hope was that you could do some kind of algebraic geometry over groups. But groups are a lot more complicated than fields, and it turns out this existential closure operation kind of maybe amplifies the complexity of the groups. So okay, so one theme of this talk will be measuring how much more complicated, or you can think of it as measuring how much more complicated groups are than algebraically closed fields. Although I'm certainly not the first to notice this. So let's meet the main character. And people online, let me know if you can't read what I'm writing.
Isabella, I'm looking at it maybe slightly bigger.
Oh, yeah. An existentially closed group. The essentially closed EC group is a group such that for any quantifier-free formula in the language of group theory, E of x m with parameters from m if P is solvable, is sort of consistent or solvable, and solved in some group containing M, then it's also solved in M. Okay, and I won't go any lower than this. Okay, so anytime any consistent system of equations and inequations, with possibly with constants, is solved in M. So they were originally studied mostly by group theorists, but then once existential closure became something that model theorists were interested in, then model theorists got involved, particularly with Angus MacIntyre. And then in the 1980s, I believe, Martin Siegler noticed a very deep connection with computability theory. It sort of came out of nowhere, and that's kind of the basis for why computability theorists might be interested in these objects. So one of the first big results from the early study of existentially closed groups through independent or in various terms, is D.H. Neumann, Angus MacIntyre, groups, and they showed that for a finitely generated group, the following are equivalent. So G has solvable word problems. So G has solvable word problems, you sort of an algorithmic condition. If and only if G embeds in every E sequence. So existentially closed groups know which groups have solvable word problems, or the class of existentially closed groups know which groups have solvable word problems. If and only if the quantifier-free diagram of G so think of this, okay, here. I think there are some undergrads here. If you haven't seen the word quantifier-free diagram before, think of this as like the word problem plus litigation. Quantifier-free diagram of G is isolated or determined by an existential formula without parameters. So there's an existential formula of group theory, which says yes or no about every element, non-element of the word problem. Okay, so we can sort of see already from the beginning that existentially close groups are a place where they're kind of algebra and model theory and computability theory all meet.
Can I ask you a question?
Yeah.
What does it mean G has solvable word problem?
Uh,
What's solvable mean?
Oh, solvable in the sense of computability theory, so that there is an algorithm which tells you, given a word, which tells you whether or not that word is in the word problem or not. So it also, like, it means that the quantifier free diagram is sizable. I should say computable. Any other questions?
Sorry, could you just repeat your answer? What's solvable, what word
Oh, yeah,
problem?
here, I'll write it down. So G has solvable word problem. Means that there's an algorithm that decides the word problem.
And the word problem is that when two words are the same?
Yeah,
Okay.
yeah, exactly, or yeah,
So,
equivalently whether a word is equal to identity or not. Or I guess I'm thinking of W and some word in the generator, so G, but it doesn't depend on the presentation if we have a finally generated.
wasn't there some result along these lines about the number of relations? With most one relation or something? Maybe I'm making that up.
I'm not sure exactly what you mean. So if you have one relation, then I think you have a computable word problem, but yeah, because there's like only one thing you can do. Okay, but if you have, I think there are groups with unsolvable word problem with like two relations, but they're certainly finally
That's fine.
presented. There's certainly finally presented groups with unsolvable word problem. Yeah, although, okay, and since we're talking about that, right, Higman embedding theorem. Okay, so if you have it would be nice if you had like a computable presentation, if that would tell you that you had solvable word problems. Okay, that's not enough because I mean, I can list the word problem, but I can't necessarily solve it. And Higman embedding says that G finally generated group has solvable word problem, or sorry.
Maybe use a better pen, the pen seems to be dying.
Yeah. This one doesn't seem much better, does it?
You can do the one over there.
Where?
Over there.
Has solvable word problem. Oh, nice.
CS pens are gonna be better than math
Right.
pens.
That's not it. I thought I said the same statement wrong. Has computable set of relators. Relating set. If and only if it embeds in a finally presented group. So we do get there are connections. I mean, this is sort of in some sense independent to the question you're asking, but it's like a very early connection between like computability, like representing something that's sort of computability theoretic in terms of something that's purely algebraic. And this last condition comes out of a sort of a step up of this Higman embedding theorem, which says that G has solvable word problem if and only if G embeds into a simple group, which embeds into a finitely presented. Kind of. Any other questions? I want to focus particularly on McIntyre's contribution to this theorem. And McIntyre showed even slightly more general than the result I'm going to state, that if T is a decidable for all there exists theory, and phi and C are partial quantifier free types, which are consistent with T, down, satisfying that phi is not computable from C, then there's a sort of existentially closed model of T which witnesses this non-computation. Then there is an EC model of T which realizes phi, no, which realizes for C and omits so in particular, if I let C be the empty set and phi be the group with unsolvable word problem that I don't want, then I can build an existentially closed group which doesn't have the group that I don't want with unsolvable word problem. But it gives us also a more complete picture of what the class of existentially closed groups look like. So what do we know so far? That if I look at all of the sort of finitely generated groups with solvable word problems, these are contained in all of the existentially closed groups. And if I give you two groups which have different Turing degree, then, okay, one of them doesn't compute the other, so I can find an existentially closed group which separates them. What we don't know yet, and what I'm about to tell you the answer to, is whether there's an existentially closed group which contains only those groups with solvable word problems, those finally generated groups with solvable word problems. I don't really, okay, so this was first observed by McIntyre. But really all the hard work was done by Charles Miller the third. Okay, and what McIntyre noticed is that every existentially closed group contains a finitely generated subgroup with unsolvable word problem. So there's no existentially closed group that just sort of sits in this intersection. Now, going back to McIntyre's result. So McIntyre shows us that if we have two finitely generated groups which have different degree, then existentially closed groups can see that difference. So it would be interesting to know, or it's a natural question. Does a relative embeddability in EC groups just recover Turing reducibility? I'm getting small, so apologies to people that are watching this. Just recover Turing reducibility. And in Ziegler's beautiful paper from 1980 or so, one of the many things that he showed, I think everyone in the room can still see this level, right? one of the many wonderful things he showed is that, no, there is, it doesn't just recover Turing reducibility, but it does recover a different notion of computability, which is entirely computability theoretic and doesn't in its definition contain anything algebraic. It is a notion of computability less than or equal to star, such that for finitely generated groups, I'm probably getting to the bottom of what I can write here. G is star reducible to H if and only if G embeds in every EC group that H does. So, a couple of comments about what this says. Comment is that I won't give the definition of star reducibility, but it is a computability theoretic reducibility. Define theory. Okay, so I should mention this is now often called sequential reducibility in honor of sequence. And it's strictly refined. It strictly refines the Turing degrees. There are star degrees which are equal to the Turing degrees, but in general, the star degrees are smaller. So the answer to this question is no, EC groups don't give us Turing reducibility, but they do give us this other purely computability theoretic notion. And so sort of flipping that on its head, I can tell purely based on the computability theoretic properties of G and H when I can omit one group relative to the other. So that's a very nice property that goes actually with groups and suggests that computability theory has a lot to say about these structures. What I was interested in is just kind of stepping back and looking at existentially closed groups, starting from a computability theoretic perspective. So Siegler really approached it as a model theorist. And so this left some questions open that I think are worth pursuing. So the first question you might ask, from a computability theoretic perspective, is like how much power does it take to build? Am I blocking people when I write on this thing? To build an existentially closed group. So remember that theorem because I'll mention it again later. Okay, but I should. Is that the existence? Well, the answer to this question is 0 prime. So what does this mean? this is sort of has two sub-theorems. One, yeah, zero prime computes an existentially closed group. And two, every existentially closed group computes the halting problem. So since I promised you constructions, let's look at the proof of one. Okay, so we'll require a little bit of background. So first, some observations. Walk people in the The first observation is just that existentially closed groups are only going to be omega homogeneous. Easy. So I don't know where does the video camera cut off?
It's fine. You actually even lower, it's fine.
Okay, awesome. So existentially closed groups are omega homogeneous.
Yes.
By which I mean, if I take two finitely generated groups, or sorry, if I have an existentially closed group, I take two finitely generated subgroups, and there's an isomorphism between them, then that isomorphism extends to an automorphism of the whole group. You can prove this using H&N extensions, if you know what these are. So in fact, what you get from the H&N is that automorphism, the automorphism that you get of the entire existentially closed group is just like conjugation by an element. Okay, so they're omega homogeneous, so I can do a back and forth argument to tell me that countable EC groups are determined up to isomorphism. By their finitely generated subgroups. And I'll call this the skeleton. If I know the class of finitely generated subgroups of an existentially closed group, then abstractly algebraically, I know what the group is. We'll talk later about whether that's true at a computability theoretic level. Okay, and then so the usual way to build omega homogeneous structures from a model theoretic perspective is to use Frécé's theorem. So Frécé's theorem tells me that if I have a bunch of finitely generated models of some theory, then under some conditions, they form the skeleton of some omega homogeneous countable model. And so what I need is a condition, in addition to the conditions that Frécé gives me, that guarantees that the model that I get is existentially. So this was first noticed by Ziegler, who showed that the class of finitely generated groups is the skeleton of an existentially closed group if and only if it's okay and existentially closed I should define what this means. It's worth noting this. This should be true for any for all there exists theory, so this isn't special for groups. K satisfies. So K is closed under substructures that satisfy something called the hereditary property. Close to the right spelling. Okay, so it says that it's closed under substructures. The joint embedding property. Which says that if I have two structures in K, then I can find some bigger structure in K which contains both of them. And the amalgamation property which says that if I have two structures in K and they have some substructure in K, which is isomorphic, then I can find some bigger structure in K, which contains both of them glued along this isomorphism. Okay, so this is enough to be a Frisé class. So this guarantees omega homogeneity. And then I need existential closure. Which essentially just says that my Frisé class, anything which I can solve in, let me write it down. Anything which I can solve in groups over a group in K, I can solve in K. What I mean by that? Of XA is quantifier 3. And solve some group which contains, let's just say B, which is a supergroup of A, which is in K. Then it's solved by some G, which extends A, and P is also in. It's not so hard to check once you figure out these are the right conditions, that this actually does give you an existentially closed Frisé class, or an existentially closed group. And then we need one more result. So Frisé's theorem gives some way of, if I have a Frisé class, so a class of finitely generated structures satisfying these properties, it builds me a nice countable structure. So it's not surprising that people were interested in the computability theory of this theorem. And it turns out that it effectivizes nicely. So I think I have to write this as a separate theorem. So this is due to Shima Karizanov. Miller. So this is Russell Miller and Montel Vaughn. And what they showed is that if A is sort of a computable Frisé class, then the model that I get out of K, so the model it determines is I showed decidable, but. So by this, I mean, at least its quantifier free diagram is computable. Okay. So you can check that this result relativizes, and if I get an A computable per se class, yeah, I'll explain what this means in words. Then the model that it builds is computable in A. So what are the conditions I need to be an A computable per se class? Okay, I should have some uniformly A computable enumeration of the elements of K. So I want to enumerate the elements of K, but A should also at the same time be able to tell me like what all the functions and relations do inside each of those elements of K. And I don't need any of these to be computable for the result that I want, but I do need a computable existential closure. So I need that if I have some phi and I have some A, then A should give me the index for G and the element of G which solves phi. So under those conditions, then I get an A computable model, and the model that it builds because I have existential closure is existential.
So Isabella, how does that then relate to your theorem over there with the zero prime? I mean, so A has to be at least zero prime.
So A is going to be, yeah, 0 prime.
Oh,
So I'll show you the class that works. One. Need to show, we'll show that the class K0, which is the set of finitely generated groups with computable presentation. So this is in the group theoretic sense. There's some group theoretic presentation for this group, which is computable, not the entire group is computable. We'll show that this is a 0 point. So I won't do that here. I should mention, so I think Ziegler first showed that it's a per se class, or that's an existentially closed per se class. And then I checked that you can do this all sort of uniformly in 0 prime. So then the effective per se theorem tells me that the 0 prime computable existential. Was that a question? I thought I saw a hand. Oh, yeah, sorry.
Is this model canonical in some way?
It's okay. It's okay, in some sense, yes. So you can generalize this construction and say, well, so these are all the finitely generated groups whose word problem is enumeration reducible. Have you met this before? These are all the finitely generated groups whose word problem can be enumerated from the empty set. So these are all the finitely generated groups whose word problem is CE. You can change that empty set to any other set, and I can define KH to be the set of all finitely generated groups whose word problem can be enumerated with an enumeration from any enumeration of, say, H. So I get like a whole class of existentially closed groups that way.
I feel like in your answer, there's perhaps something implicit. Let me confirm it. Is the model given a Price class? Is the model that it builds, like, is there a unique model with that?
Yeah,
Price?
yeah. So sort of by virtue of it being omega homogeneous, you can do a back and forth construction. And so if you take any two countable models, which both have the same skeleton, then they're going to get. And I guess this is also, so I think if you take any existentially closed group, which is contained in this group, then it's going to be again isomorphic to this. It's sort of minimal in some sense. I think I have 10 more minutes. Well, I'm supposed to end at 40 past, right?
I believe so.
Okay, cool.
Yes, you have 10 minutes.
Okay, cool. Okay, so that's one direction, and then the other direction is well, I want to show that every existentially closed group computes zero prime. And essentially what I'm using is that checking consistency in groups has to be a zero, is like in general a zero prime question. So let me make that slightly more explicit. So I'm going to take a finitely presented group. Let's go back to one of the questions at the beginning. Whose word problem computes zero prime. You can show one exists using Higman embedding theorem if you don't believe me. Well, then I guess you have to ask if you believe Higman embedding theorem. Oh. So let's call this group F equals generated by F. So R is a finite set of words. And then I can take the formula for every word W. BW will say, does there exist an X such that all of these relations hold of X, and W doesn't hold. That notation, but they were over the relations that are. This is consistent if and only if W does not equal 1 in F. And to check whether or not W does not equal 1 in F, I'm going to have to solve the word problem. So to determine whether or not I realize this existential in any existentially closed group that I build, I'm always going to have to solve the word problem of any finitely presented group, in particular one that computes zero prime. Okay, so this tells me that building an existentially closed group in general requires at least zero prime. I know it's exactly zero prime because I can do one in zero prime. But this construction doesn't tell me that I actually always get a finitely generated subgroup of degree zero prime. I don't necessarily embed this finitely presented group. And in fact, I can't, right? Because it has degree zero prime, and Neumann-McIntyre-Rips tells me that there's going to be some finitely generated, or sorry, some existentially closed group which emits this. So this raises the question of whether this is the theorem that I just erased. It says that existentially closed groups are a zero prime phenomenon in some sense, whether that's locally true. So does every existentially closed group contain a finitely generated subgroup of degree zero prime? Okay, so a positive answer would be sort of interesting because it would tell you that the complexity of the whole existentially closed group is like realized by some small piece of that group. And a negative answer would also be sort of interesting because it would tell you that somehow, maybe all the pieces that you need to put your existentially closed group together are all sort of not very complicated. But when you put them together, they have to build something which is more complicated than each of the individual pieces. So it turns out the answer is no. Let's phrase this like this. There is an EC group. Necessarily compute zero prime, but all of whose finitely generated subgroups are below a given PA degree. So I'll explain what PA degree means in a second for those of you who don't know, but let me just make sure that the quantification is understandable. So I give you a PA degree, or first you give me a PA degree, and then I build for you an existentially closed group. All of whose finally generated subgroups are computable in that PA degree. Okay, and what is a PA degree? So a PA degree is a Turing degree, which computes a complete extension of piano arithmetic. Degree A is PA if it computes a piano arithmetic. Equivalently, I'll need this in a second. Equivalently, if it computes a path in every computable infinite binary tree. Okay, so before I talk about how one proves this result, quick discussion of what this means. So in general, PA degrees, because I'm assuming my audience is fairly general here, so in general PA degrees, there are PA degrees which are in some sense quantifiably considerably below 0 prime. So this is sort of a somewhat strong no to this question. I know from this theorem of McIntyre and based on the work of Miller that I can't get computable. So in some sense, getting something which is low is like as good as I can do. And actually, if you look in detail at the Miller results and the McIntyre results, they do show that actually every existentially closed group computes has a finally generated subgroup whose degree is a PA degree. So this is best possible. So this. By I know it's true, I should say. And it also kind of suggests that Miller's proof can't be improved. That's sort of a separate discussion. PA degrees can be low. I put that in quotation marks. I guess I don't need to. Compared to 0 prime. So this is a no answer to that question. I don't think I'm going to give the proof in 1 minute, so I will not talk about the proof of this. So I'll just very briefly sum up what we've done so far. Okay, so for one thing, let's put here. There's a corollary. There's an existentially closed group, which necessarily computes 0 prime, but all of whose subgroups are low. Since there's a minimal pair of PA degrees, it tells me that there are 2 existentially closed groups, such that the only finitely generated groups which embed into both are finally generated groups with solvable word problems. So this theorem of McIntyre and McIntyre, Neumann, and Rips, right? You couldn't realize this this central piece with one existentially closed group, but you can do it with two. There are is okay. With the right interpretation of minimal pair of EC groups. I'll skip the last corollary right here. And so this is the picture of what we know about existentially closed groups based on what we've seen so far. So here's the computable sets. Here's 0 prime. I know that existentially closed groups live up here. I know that if I just want to get some omega homogeneous, I just want some first A class of groups. Okay, well, we didn't talk about this, but you can do this using, you can build a computable first A class of groups. So, as soon as I insist this first A class is existentially closed so that I get an existentially closed group, then I go up to the PA degrees. But somehow that's still far below, in some sense, what it actually takes to build an existentially closed group. So there's sort of a nice stratification of the complexity of building an existentially closed group that computability theory tells you. So I'll stop there.
Questions?
Yeah, what happens if you change the setup from, looking at the quantifier free diagram like you did to only looking at positive formulas? Is it a lot different? You know, just equations, no inequations like.
That's a good question.
Why shouldn't it be? It's easier to build models.
Yeah, and in some sense, that's sort of a natural thing to do because I didn't talk about it, but there's a relativization of my first theorem, which is in the enumeration degree, so where you're only really given positive information. Let's see. Yeah, I mean, I think something, I would expect something nice would happen, but I don't know off the top of my head exactly what. So I mean, in general, these things, like, I think they can have total degree, so you could just get something where the positive part is enough to compute the negative part. I don't know, I should stop. I should not say things that I don't know the answer to.
I mean, if you just have positive information, I mean, can't it be like that the trivial group is like
Oh, I see.
positive, close
wait,
in that sense?
Wait, are you saying like when I define existential
Yeah.
closure? Oh, I see, in that sense. Yeah, so actually it turns out that for groups, it doesn't change. Okay, the trivial group is the one counterexample, but for every other group, if defining existential closure where you only consider the positive things is the same as doing everything.
Oh, it's the same.
Yeah,
Oh.
yeah.
Other questions? Now let's thank Isabella again. There's some coffee in the back, partially delivered by me. And if you were planning to go to dinner and didn't have your hand counter, why don't you just come let me know? So I could call the restaurant and let them know.